In this lesson, we'll be discussing how to evaluate limits at infinity of polynomials. Please check out our other videos on how to evaluate limits of different types of functions. Now, evaluating limits at infinity of polynomials. If you are given to evaluate the limit as x approaches infinity, meaning as x gets larger and larger, of 3x squared minus 5x plus 1. How do we evaluate this? There's one rule to apply, and that rule is simply consider only the term with the highest degree, and we can see here the term with the highest degree is 3x squared. The rest become insignificant. That implies that what we'll have left will be the limit as x approaches infinity of 3x squared. So as x approaches infinity, we do a direct substitution. We are going to have 3 multiply infinity square. Infinity square is still infinity. Multiplied by 3 will still give us infinity. So this is the final answer. Let's take another example where you have the limit as x approaches infinity of 3x cubed minus 5x to the power of 4 plus 2x. The same method applies. You may want to pause the video and try this out. Consider only term with the highest degree, and that will imply that what we have left will be the limit as x approaches infinity. The term with the highest degree is minus 5x to the power of 4, so we have minus 5x to the power of 4. As x approaches infinity, we do a direct substitution. We are going to have minus 5 multiply infinity raised to the power of 4, and infinity raised to the power of 4 is still infinity. Multiply minus 5 will give us minus infinity. This is the answer. Let's consider rational functions. Where we have rational functions, how do we evaluate the limits at infinity? Given a rational function, f of x is of the form numerator all over denominator. There are 3 cases to be considered. The first case is where the degree of the numerator is equal the degree of the denominator, and the second case is where the degree of the numerator is less than the degree of the denominator, and the third case is where the degree of the numerator is greater than the degree of the denominator. You have been told that there are 3 rules that apply, but those 3 rules can be summed into one, meaning you can only divide by the highest degree. In all 3 cases, this method will work. But before we take some examples, let's give an overview of the possible results of each case. In the first case, we will always have the result to be uh, the leading coefficients, the ratio of the leading coefficients. So here we have the ratio of leading coefficients. And in the second case, we will always have it to be 0 where numerator is less, so it is bottom heavy. The third case, we will have it is top heavy plus or minus infinity. This will always be the output. Let's take some examples. Given that the limit as x approaches infinity of 2x squared minus 5x all over 8x squared plus 3x. How do you evaluate this? Remember, we can always apply the shortcut, which is the first rule. Consider only terms with the highest degree on both sides. So it will imply that we will have the limit as x approaches infinity of x squared, which is the highest at the top, all over 8x cubed. And if we go further to evaluate this, we'll see that this can cancel out this, and we have 2 all over 8, which will give us 1 all over 4. If we look at our possible outcome here, where the degree of both sides are equal, you see the ratio of the leading coefficient will always give us the output, will always be the output. Okay, let's try this rule here, which we have the general rule, and let's see if that still works. Okay, now if we apply that general rule, we will have that the limit as x approaches infinity of 2x squared minus 5x all over 8x squared plus 3x, meaning we divide both sides by the highest degree, and here the highest degree is x squared, the same thing here, x squared. All right, and we will have, if we distribute, we are going to have the limit as x approaches infinity of 2x squared all over x squared minus 5x all over x squared all over 8 x squared all over x squared minus 3x all over x squared. And this will give us the limit as x approaches infinity of, this cancels out, we have 2 left, minus this cancels this out, we have 5 all over x left, all over this cancels out, we have 8 left, minus the same thing here, this cancels this out, we have 3 all over x. Now let's do a direct substitution. As x approaches infinity, we are going to have 2 minus 5 all over infinity will give us 0, because any constant divided by a very large number. Let's take, for instance, 5 divided 1000 is going to give you 0.00. So increase it, 5 divided 1 million, so it's going to give you still 0.00 and so on. So this gives us all over 8 minus 0, which is the leading coefficient, which is 2 over 8, which is equal 1 over 4. You see, the shortcut always works anytime, any day. Let's take another example. If you are given to evaluate the limit, okay, we can still do it here. If you are given to evaluate the limit as x approaches infinity of 4x cubed minus x plus 2 all over 2x cubed minus 5x minus 1. How do you evaluate this? You can go ahead and pause the video before watching the solution. The shortcut that you can always consider is disregard irrelevant or insignificant terms so that you are left with the limit as x approaches infinity for the top 4x cubed all over 2x cubed, right? And we will see what we have left. This can cancel this out, right? So that we have 2 left. So if we check the result which we have here, that will always have the ratio of the leading coefficient as our final answer. So which is what we have here, because what we have here is 4 all over 2, which is equal to. So this is correct. Let's take another example. Before we take another example, let's try the long method and see if that is applicable here. Let's try the long method, which is we divide by the highest degree. So we are going to have the limit as x approaches infinity of 4x cubed minus x plus 2 all over 2x cubed minus 5x minus 1. Both sides will be divided by the highest, which is s cubed, right? So we have 1 all over s cubed, 1 all over s cubed. If we distribute this, what we have exactly here will be the limit as x approaches infinity of 4s cubed divide s cubed minus x divide s cubed plus 2 divide s cubed all over 2x cubed divide s cubed minus 5x divide s cubed minus 1 divide s cubed. We can see here that this can cancel out, so that what we have left will be the limit as x approaches infinity of 4 minus this will cancel this out, so that we have 1 all over s squared plus this. Okay, it doesn't cancel out. We have 2 all over s cubed. Everything all over this cancels out. We have 2 minus this cancels out. We have x squared left, so we have 5 all over x squared minus 1 all over x cubed. So as x approaches infinity, we do a direct substitution. We are going to have 5 minus 1 all over infinity square will give you 0, plus 2 all over infinity cube will give you 0, all over 2 minus this same 0 minus 0, so that we still have the ratio of the leading coefficient, which is equal to. So you see the shortcut works anytime, any day. Let's take another example where the degree of the numerator is less, and the possible output is that we will always get a 0 result. And let's see if that is correct. Given to evaluate the limit as x approaches infinity of 3x squared plus 1 all over x cubed minus x. Let's apply the same rule. The first rule for polynomials, which is consider only the terms with the highest degree, which implies that what we have left will be the limit as x approaches infinity of 3x squared all over x cubed. All right, and we can see that this can cancel out completely, and cancel here. We have 3 all over x left, so that our final answer here will be the limit as x approaches infinity of 3 all over x. So as x approaches infinity, what we'll have left will be 3 all over infinity. And you remember, any number divide infinity will give you 0. All right, so this is in line with the summary result we have here. If the degree of the numerator is less, you will always obtain 0. Let's try the long method here and see if that still works. So we are going to have the limit as x approaches infinity of 3x squared plus 1 all over x cubed minus x. Remember, we multiply both sides with the highest degree, and the highest degree is x to the power of 3. We divide both sides. So we are going to have 1 all over x cubed. The same thing here, multiply 1 all over x cubed. If we expand, all right, we are going to have the limit as x approaches infinity of 3x squared all over x cubed. X squared will cancel out, so that we have 3 all over x left plus 1 all over x cubed all over x cubed. Divide x cubed will give us 1, right? Minus 1 all over x squared. So as x approaches infinity, we can now do a direct substitution. We have 3 all over infinity, which will give us 0, plus 1 all over infinity cube will be 0, all over 1 minus 1 all over infinity square, it's 0, so we have 0 all over 1, which is 0. So the shortcut works perfectly well. Let's take another example where we have the degree of the numerator higher than the degree of the denominator, meaning it is going to be bottom heavy. It's going to be top heavy. We have done bottom heavy now. So where it is top heavy, remember the summary of the output will be plus or minus infinity. Where the degree of the numerator is higher, we are going to always have plus or minus infinity. So let's take this example. If you are given to evaluate the limit as x approaches infinity of 2x to the power of 4 minus x all over x squared plus 3. Remember the solution, you consider terms with the highest degree, which will imply that all we have left is the limit as x approaches infinity of, for the top we have 2x to the power of 4 all over x squared. And this will give us, we'll see that these can cancel out this completely, so that we have 2x squared left, right? So as x approaches infinity, we are going to have, this is the limit as x approaches infinity of 2x squared. And as x approaches infinity, it will imply 2 infinity square, which will still give us infinity. All right, so we see when it is top heavy, the answer is always plus or minus infinity. Let's try the long method, which is applying this method. Divide both sides by the highest degree. We divide both sides by the highest degree. So this will imply that we have the limit as x approaches infinity of 2x to the power of 4 minus x all over x squared plus 3. So both sides will be divided by the highest degree, which is x over 4. To the power of 4, x to the power of 4, uh, x to the power of 4. If we distribute this, what we are going to have left will be, we are going to have that this can cancel out this completely. We have 2 left minus 1 all over x to the power of 3 divide this can cancel out 2 here, so we have 1 all over x squared left plus 3 all over x to the power of 4, right? That is what we have left. So let's solve this properly now. We see that we are going to have the limit as x approaches infinity of 2 minus 1 all over x cubed all over 1 divide x squared plus 3 all over x to the power of 4. So as x approaches infinity, we do a direct substitution. We are going to have 2 minus 1 all over infinity cube will give us 0. All over 1 all over infinity square will give us 0. My plus 3 divide infinity to the power of 4 will give us 0. So we have 2 all over 0 left. Now be careful. This is where students make mistakes. 2 divide 0 mathematically is undefined or does not exist. In terms of limit, this uh, tends to infinity. If it's negative, then it becomes negative infinity. So infinity is our final answer, and that is what we also have when we apply the shortcut. You see that the shortcut always work. Let's take one more example, applying both the shortcut and the long method of evaluating the limits at infinity, applying this one rule, which is dividing both sides by the highest degree. If you are given to evaluate the limit as x approaches infinity of 5x to the power of 5 minus 2x cubed plus x all over 3x squared minus x plus 4. You may pause the video and try your hands on this. The same method, the first rule, disregard other terms except the term with the highest degree. On both sides, we have the limit as x approaches infinity of 5x to the power of 5 all over 3x squared. This is what we have left. And x squared here will cancel out x squared from here. We have x cubed left. So in the end, what we have left will be 5x cubed, right? Which is the limit as x approaches infinity of 5x cubed all over 3x, all over 3, and this will give us as x approaches infinity, we are going to have 5 infinity cube. So 5 multiply infinity cube all over 3. All right, and this will give us now a very large number, very large number divided by only 3. You will still get a very large number. You can imagine 10 million divided by 3. Now see 20 million divided by 3. Each will get very large number. So, and the large number we are talking about now is infinity. So this gives us infinity for the short, using the shortcut, right? Let's try the long method, which is applying this, dividing both sides by the highest degree. Let's see if that works. Now this will imply the limit as x approaches infinity of 5x to the power of 5 minus 2x to the power of 3 plus x all over 3x squared minus x plus 4. Dividing both sides by the highest degree. The highest degree is x to the power of 5. So let's divide both sides. So we are going to have 1 all over x to the power of 5. The same thing here, 1 all over x to the power of 5. And if we distribute, we are going to have the limit as x approaches infinity of 5x to the power of 5 all over x to the power of 5, right? Minus 2x cubed all over x to the power of 5 plus x all over x to the power of 5 all over the same thing we have here, 3x squared all over x to the power of 5 minus x all over x to the power of 5 plus 4 all over x to the power of 5. And if we continue to evaluate this, we see that this will cancel out this. What we have left will be the limit as x approaches infinity of 5 minus, this can cancel out completely, leaving x squared here. So we have 2 all over x squared plus x all over x to the power of 5, everything all over The same thing here. This can cancel out, leaving s cubed here. So we have 3 all over s cubed minus 1 all over x to the power of 4 and plus 4 all over x to the power of 5. So as x approaches infinity, we are going to have 5 minus 2 divide infinity square will give us 0, right? So we already established that we have 0. The same thing here, plus 0. All over here we have 0 minus 0 plus 0. In the end, we have 5 all over 0 left, which tends to infinity. Remember, we said mathematically you can divide by 0, and in terms of limit, does not exist, it's undefined, and this tends to 0 in terms of limit. So this tends to infinity in terms of limit. Please, if you find our videos helpful, we will appreciate if you subscribe, like, and share so that we can provide more videos to reach out to a larger community. Thank you for watching.